Hi and welcome back to Properties and Structures of Matter, and we're looking at the final inquiry question, which is bonding. And today what we're looking at is different types of bonding that we have. Now, we've talked about a whole range previously already, and our main types of covalent molecular substances, the type of bonding that's present in between those, are really the result of two main types of bonding. The first one being intermolecular and the second one being intramolecular. So if you're looking at the diagram that I have here below, you can see here the attraction between the two atoms in the molecule are an intramolecular attraction, think intranet, so within our school, and then the bonds between different molecules. So here's one molecule of hydrochloric acid and here is another molecule. Those bonds in here between are our intermolecular, so the internet. So within our school, it's the intranet working around in our school environment, and then we connect to the internet in somewhere else. So we're going to go into, over the next couple of videos, more detail into each one of those types of bondings, and there's several within each class as well. So what we're going to look at first of all is our intermolecular forces. So our intermolecular forces exist between our molecules. So they're the attractive electrostatic attraction between holding our molecules together. So what we're looking at here is the attraction between the positive and the negative ions in those molecules. Now, if we look in ionic lattices, it's a positive and negative attraction there, but in covalent bonds, it is the shared electrons in the covalent bonds. So we're looking there and going, well, it's same with intermolecular, so between the molecules there is still an attraction between the positive charges and the negative charges in the molecules to other molecules, and that's usually due to an uneven distribution of those electrons. When we talk about some of these properties, these intermolecular forces, you can see some of these in play in everyday life, like our soap bubbles, and the fact that those soap bubbles are able to hold together is a result of those intermolecular forces. And for any of these forces to, or any of our covalent molecules or so forth to melt or boil, those forces between the bonds have to be broken. Now, in this video today, we are going to look just at one type of bonding to break up that learning into manageable chunks for you. But there are three main types of intermolecular bonding. So these are the three types of bonding that can occur in between each of the molecules that we have. So they are dispersion forces, dipole-dipole forces, and hydrogen bonds. So the one that we are going to focus on today in today's video is the dispersion forces. So these dispersion forces are very weak. They are very weak, and they occur between all our covalent molecules. So the reason that we have this is it's due to the constant changing in the distribution of the electrons in the nearby molecules. Now, if you look in our diagram that we have over here to the right, you can see the position of the electrons here. So they are temporary. Their positions are temporary because, remembering, our electrons are moving around in that cloud all the time, and they can be in a variety of different places. So if we look in our diagram here, they are over, the electrons are all over towards the left-hand side there, creating a negative side on that side of the molecule, and there's an uneven distribution, making the other side more positive. And then we have here, they could be in evenly distributed, making it more positive on one side, more negative on another, or it could be even and it's therefore neutral. So if they are, they can actually even then induce a dipole in a neighboring atom as well there. So what's happening is there's a constant change. It's a temporary dipole. They might be on one side at 1 minute and the next side evenly distributed on the other side in another. So that dipole is constantly changing there, and that is making those forces constantly changing. So it's affecting the structure, and we'll talk, or the forces and so forth, and we'll talk about that in a minute. So because these electrons are in constant random movement, they could be anywhere within that electron cloud, the electrons can be evenly distributed. So that makes it a temporary dipole rather than a permanent dipole. And it also is quite short-lived. They can be moving in one instant in one place, in another instant in another. So they're constantly being formed. These bonds are constantly being formed, and they're constantly being broken. So these forces are relatively weak, and these forces arise from that electrostatic attraction between the positive charges and the negative charges between the molecules, and again, instantaneously forming and instantaneously breaking. Now, these dispersion forces can be heard under a variety of different names, and different textbooks will call them different things, different internet sites and so forth. So it's important that you're aware that they may come under different names. They can also be called van der Waals forces. It can be called an induced dipole, where it induces a dipole in another neighbouring molecule. They can sometimes be called London dispersion forces. They're all names for the same type of force there. Now, one thing you're going to notice is the magnitude of that dipole, and therefore the strength of its attraction, is going to increase as the number of electrons in that molecule increase. So as the size gets bigger, the strength of the force will also increase. So having a look here, this is bringing back to that diagram I was talking about before and how they can move. Here they're both evenly distributed. Here we've got an instantaneous dipole. You can see this side has a greater number of the electrons on this side versus this side, and this one is evenly distributed. So what's actually happening here is the negative sides on this side creating a negative dipole there, and on this side it's a positive. That's then drawing the electrons from this electron cloud to this side in that attraction, and that's our electrostatic attraction that we're experiencing there, causing those two molecules to come together. Now, interestingly, looking at that example we talked about before, being the number of electrons present in the molecule or the atom, affecting the size and strength of this bond, we can see that here with chlorine. So if I had chlorine, a chlorine molecule, so Cl2, hence it would have 34 electrons, it's got a boiling point of negative 35 degrees Celsius. Compare that to bromine, which has in its Br2 molecule, so if we think this is Cl2 and this is Br2, if we're looking at that, it has 70 electrons. Its boiling point is much higher. So more energy is required to break this bond than this one. So more energy is required due to, you can see the increase in boiling point, and that comes down to its structure, which is 70 electrons in and around that molecule versus 34. Now, not much energy is generally required to break the bonds, and even 59 is relatively low. Compare it to water, for example. So it's still not a lot of energy, so they're relatively weak bonds. Now, our non-polar compounds, and we're going to talk about that in our next video, our non-polar compounds with only dispersion forces, no other type of forces in them, will have generally a relatively low melting point and boiling point there. So what I'd like you to do is go and do the couple of questions on Education Perfect that match this video, and we'll have another one ready for you shortly. See you then.